Someone pass me into the grave. It's a shame.
Now that you're at least aware of how the unit circle works in terms of this or that times that equals that, or basically sine, cosine, tangent, arctangent, secant, cosecant, that type of thing. I've laid out for you in a program called Geometry Sketchpad a way to kind of look at, investigate, and truth, what you know or suspect is true from survey, that is the small angle approximation. So I've laid out here is not a unit circle, but if you look at, this is not the slope, but the length of CA. I'm going to push this, make this go forward a little bit here. Grab this point. I have laid out an animated circle using something called parametric design. So we stop that right there. And we see that the circle is 10 in length. CD measures the sine. In all reality, it's DC, which you really want to think about. And AD remembers the calculates the cosine, and CE the tangent. And these are all the geometric economic calculations. You know that CD divided by AD times AC equals CE. You know that sine over cosine times the hypotenuse of the tangent, or just sine over cosine. It's a unit circle. This is a 10-unit circle. Looking right here. So what I'm going to do is we're going to test the small angle approximation by watching down the small angles, how the radians, the length of CD and the length of CE approximate each other and make a call there at two places, what we will call a small angle. Again, you've done that in survey, so I'm going to push this forward here. I'm going to slow it down a little bit, and we'll investigate the very small angles. This is a program called Geometry Sketchpad. It's $10 for a 1-year license, $30 for a perpetual license, and that allows 3 seats. It's got a little bit of a learning curve to it, but not that bad for those who are interested. You can do the same thing in parametrics in AutoCAD, but the animation is not quite as easy to do. Bring down the speed here and let that come down to a little work on this. And right now you see, as it goes through there, right around here, things start to look about the same. I'm going to stop it just on the other side. Right there, we've got 0.07 radians, and if you divide CE and CD by 10, you've got 0.07. This number of radians here is listed to just 2 places, and these are listed just to 2 places, so they are the same. We're going to go ahead, stop it there. Right around there, they start to diverge. We're at 0.25 radians. I can actually change and reverse that. I'm going to bring it back. Pause it right there. You're now flipping on the other side, so it goes a little odd. I'm going to turn it on. Flip it back, flip it back, flip it back, flip it back, flip it back. Stop it right there. At 0.12 radians, which is a little bit more than 5 degrees, you see again the approximation looking pretty good here. AD being the cosine, we'll check that out, I'm sorry, is the cosine. You see that swings away a little bit more, so that approximation is not as good as that for the small angle approximation. So once again, if you measure in radians, a radian being defined as the ratio of the arc length to the radius, a radian having 2 pi of themselves inside a circle at small angles, the tangent and the sine are equal to the angle, and in this depiction you can see effectively what happens to the tangent out there at that theoretical infinity, or I'm sorry, 90 degrees. We'll flip it again in a second here. You see it's going to one direction, now to the other. It's getting longer and longer. You know these things, and you start to learn calculations. You want to learn to visualize this. Basically, this is a linkage. If you want to learn the word, this is something kind of like a linkage. I'm going to stop it right there. Continue. Stop it there. You're getting close to that ratio of 1 to 1. Stop it there. You're getting close to that ratio of 60 degrees. Stop it there. You're getting awfully close to that ratio of at 90 degrees. You see that bit there. I'm going to stop it again. This time I'm going to stop it and see how long this calculation will take us. See how close we can get to 90 degrees. Remembering that this is basically what trigonometry is. It is not just the triangle, it's the triangle changing within the circle. You learn the unit circle, so you have some checks on the software that does pretty neat stuff for 10 bucks. You also start to realize how one thing begets the other, how the derivative and then the integrals affect each other, how sine is related to cosine and cosine is related to sine and tangent is related to both. I'm slowing it down here. I'm going to stop it as close as I can when that thing starts to really head off to, ooh, it already flipped back. If you notice there, it flipped back. So you can get this. It does head off to infinity. We'll look at that. Thanks for listening. Now, it would appear a capture, whoa, handheld of a calculator with, right, we're going to zoom out here, calculator, TI-83 plus, zooming into the screen, see what we got here. We're going to hit second quit, and then look at program A and see what this does and see how it picks up. The concept here is animation. There it is. There's a circle. And it looks like that's another circle. And that's another circle. And that's another circle. And what you're doing is you're actually drawing a series of short lines which are defined at points defined at 15-degree increments. Of course, we remember that 15 degrees is the same as a time zone. We remember the cosine of 15 degrees is 0.9659 and the sine is 0.2588. We remember that we could have just converted it to radians. We would have been only about 2% off at 15 degrees if we would have known that the cosine is 1 minus the angle squared and the sine is the angle. And of course the tangent is the sine over the cosine. But we do all that so we can realize that animation and use of trigonometry is not something mystical. It is something that actually people do all the time in high school math class when they're not paying attention to what they're not paying attention to. So let's look at the program. Second quit. Go to Program, Edit. That's how long that program was. What it did is it actually began by clearing the screen, declaring that everything would be in radians, making a matrix. That's going to be X, Y, Z with a 1 dummy and putting it into matrix B. That's how you make a size of a matrix in TI Basic. And then looping through from 10 to 20 for K and from 1 to 24 for the other. That was the radius. It actually did the formula for all those different circles and then printed them, drawing lines through in the matrix. So it had a bunch of loops, and we'll take a look at something like that, but realizing that if we can store things in a matrix that is 4 rows with a dummy in the end, it's going to be pretty straightforward to map traverses or anything where you can connect lines by connecting points. And that makes it possible to go all of a sudden and do some sort of transformations on that by multiplying by the 4x4 transformation matrix. All right, let's see how this works. We're going to upload this and see how it all goes.